All right, so we have taken DNA, turned it into mRNA, turned that mRNA into a protein. Now, anywhere along the way, we can have mutations. And mutations are changes in the genetic information. So it can either be changes that happened when we replicated the DNA that weren't caught by DNA polymerase. It can be changes that are made in the mRNA because we transcribed it wrong. It can be changes even made in the translation. It can be, and those changes can, also after you transcribe something, there are things called mutagens, which are chemical agents or physical agents like, UV rays that can actually change your DNA and mutate it. Okay. So we're going to look at the different types of mutations. But first of all, why is just changing one little nucleotide a big deal? Well, hemoglobin is the protein in your blood that carries oxygen, and normal hemoglobin has the DNA sequence of CTT, which transcribes to, GAA. GAA translate to a protein called glutamine. Now, if you just change this one nucleotide, this is called a point mutation. If you just change this one nucleotide and instead of a T, you have an A, that's going to pair with a U on mRNA and it's going to make valine. So what happens is you have a misshapen hemoglobin, all right? And this causes sickle cell anemia. So sickle cell anemia means that your blood cells are shaped like a sickle instead of like a lifesaver, okay? And so anyway, and so there are disadvantages. This can carry a lot less oxygen. And depending on how many of these you have, you can have all sorts of other medical issues, like sickle cell crisis and things like that. Now, if only half of your cells are shaped like this, you will still have an issue with oxygen transportation, but you will also be immune to malaria. So that is definitely an advantage, although having the low oxygen is a disadvantage. So it kind of evens out, I guess. All right, so let's talk about these types of mutations. So first of all, we can have our point mutations. These are all going to be point mutations. All right, that means just one nucleotide is changed. All right, so this is our normal gene that we're coming, and the normal DNA, and then normal mRNA and normal protein. So if you look here, you can see that accidentally, when we made the mRNA, this should be a C and goes with a G. Instead, we changed it to an A. So we substituted the wrong letter, and we ended up with the wrong amino acid, which is going to mess up what the protein looks like. All right. So if you look here where we have UUU, we're supposed to have UUU, but instead this U got lost somewhere. This causes a frame shift mutation because remember, if we substitute a letter, I'm going to go back here. If we substitute a letter, depending on what we substitute, we're going to talk about that in a minute, could make a big difference or no difference at all. But if we delete or we insert an extra nucleotide, this is going to cause the entire codon sequence to shift, and that's called a frame shift. So if I add an extra one, so for instance, let's look up here real quick. All right, I'm going to erase this. All right, these are read in threes. So this is one codon, one codon, one codon, one codon. If I take out this U, then actually I have, this is now my codon. And so the entire rest of the protein, or the entire rest of the mRNA, has been shifted by one nucleotide. Okay? So that instead of making phenylalanine and glycine, I'm making leucine and, quite frankly, I'm not sure that one. But either way, I'm shifting everything down one. If I insert something, I am shifting everything this way by one. And it is going to basically change everything going forward from this deletion or insertion. So this next picture, all of these pictures are in your notes, by the way. So a substitution is where we change one nucleotide. A deletion or an insertion, those are big problems because then we have shifted the entire frame. And now we're going to create probably a completely different protein. All right. So this is a substitution right here. All three of these are substitutions. All right. So if I substitute, in this case, we have an A. We should have oh, okay. I'm sorry. They're just showing you the mutation. So this one is mutated. It's an A and it's supposed to be a C. So that actually is going to result in the exact same amino acid that, CUG translates into the exact same amino acid as CGG. All right. So this is silent. In other words, it's not going to make a bit of difference because the amino acid that is created is the exact same. All right. Now, here in position 14 of the DNA, we have an A. We should have a T. So that's what we should have. If we had a T, then we would have an A right here. That's what we should have. But instead, we have a U. In that case, the amino acid is changed. It should be asparagine, I think, instead of valine. Or it should be asparagine, but instead it's valine. So basically, this has changed the amino acid, and it makes something called missense, which basically means we just changed out an amino acid at one location. Okay, so all of these amino acids are going to remain the same. And if this chain kept going and didn't stop, every other amino acid would remain the same. And it would be one amino acid change, just like we saw in sickle cell anemia. So sickle cell anemia is an example of a missense mutation. Now, a nonsense mutation is essentially when we have a mutation, a point mutation that codes for a stop codon. So that means that the protein doesn't get made or it cuts off prematurely because we accidentally created a stop codon where there should have been more amino acids. Once that tRNA hits a stop codon, it's going to stop creating an amino acid chain. It doesn't matter what comes after it. Okay. So when we created the stop codon right here, we're missing out on all of these. They don't get translated. All right. And so that's a big, huge problem. So that's a nonsense mutation. Now, everything else that we described in insertion or a deletion is actually going to shift the reading frame down or forward or down so that completely different. So translation is going to continue, but everything after the addition or deletion is going to be incorrect. So all amino acids will change beyond the point of insertion/deletion. All right. And this is definitely going to change the protein. This changes the protein created. This doesn't create a protein at all. So no protein is made. This is going to also change the protein. All right. So a silent mutation is the only one that's not really going to make any difference. Okay. Also, another thing is, and just a side note, that mutations that happen in introns, because introns are not coded for proteins, they don't make any difference. So that would also be an example of a silent mutation.